Alright, hello, this is Andrew again, back with another video. This video here is about how to use the JVN Mechanical Design Calculator. It's a tool created by a gentleman named JVN of FRC Team 148, the Robo-Wranglers. He's made a few of them now over a few years, and I think it's a really useful tool that I want all my students to know. And for anyone who doesn't know how to do it and wants to learn how, I think this would be a good instructional video on how to get it done. So this is going to be your main window. I have it open in a Google Spreadsheets. It's usually an Excel file. You can transfer it over. On the link of this video, I'm going to have a Google Spreadsheets share button you can click so you can get your own version. I prefer Google Spreadsheets just so I can access it wherever, but whatever works for you. So if you get to your first page, this is going to be the first tab. It's going to be a README. It has some info on how you get through some stuff. I'll let you read it on your own time. Right now, really not much to do here. The second tab is called Custom 2-Speed Drive. It's essentially this is a drivetrain calculator to show you if you use certain motor and gear combination, provided the weight of your robot and certain other variable factors. Here's what speed you should expect. I'll go through each one by one, and then I'll show some examples. So the first option you have here, it says sim. This is actually a drop-down menu. It lets you choose what motor you have. So if you want a mini sim drivetrain, a sim and a mini sim, bag motor 775 Pro. It has all the stats for them. So if I want to go to a bag motor, you can see the free speed, stall torque, stall current, free current, all that stuff gets affected. It all pulls from a different database in another tab. For now, I'm just going to use sim. I don't really need to worry about these numbers. It's nice to know them, but as long as the spreadsheet has it all right, you don't need to worry, and the spreadsheet does have it all right. The real-life speed loss constant, essentially in a drivetrain, what Mr. Noon has found is that over the course of driving and a bunch of mechanical errors, you're not going to get 100% of your energy that you put in, because that's simple thermodynamics right there. But he says his experiments have shown about 81% of what you put in, you get out. So that's used to find you take your mathematical outcome, whatever your speed the math says you have, which we'll go over in a second, and that right there is just going to be that's going to be your ideal. That's going to be what you'd like it to be, the perfect world. But we have friction, we have imperfect mechanical devices. Terrible wording, I know, but just work with me. Point being is we have your theoretical speed that is like the maximum, and you have your quote-unquote real-life speed. Of course, everyone's going to use a different speed loss constant, so if you're comparing different drivetrains, or if you're telling people about your robot, tell them the free speed, tell them what the theoretical is, because that's going to be the same for everyone. The math is the same for everyone. Next one is drivetrain efficiency, and that sort of helps along with free speed. And that's just going to say, okay, in the end, like, you may lose 10% just to miscellaneous reasons. I usually don't touch these. Excuse me. Yeah, unless you really know what you're doing and you've done your own tests, I wouldn't touch them. Over here, I would touch this. Number of gearboxes in drivetrain and number of motors per gearbox. That's going to tell you, it's pretty self-explanatory. It's going to say, alright, let's say I have a theoretical West Coast drive. I have 2 gearboxes, one on either side, and I have 2 motors in each. So that's going to be a total of 4 motors, 4 and 4 sim motors in this case. Just a note, if you choose an option like one sim and one mini sim, then that's going to count as one motor, quote-unquote motor, because it's combining them. So if you have a sim and a mini sim and you say 2 per gearbox, you're really saying each gearbox has 2 sims and 2 mini sims. So just a thing to make note of. Most drivetrains, the setup, 2 gearboxes, 2 sims, and a 4 sim drivetrain total. That's fine. It's going to get you through World Championships. Your total robot weight is exactly as it is. 120 pounds is the maximum robot weight. It's usually nice to design around the maximum. Of course, then we add in 14 pounds for a battery, 20 pounds for bumpers. Ends up being 154 pounds. Not sure why this one says 150. weight on driven wheels, essentially like, okay, do you have casters or do you have anything that's non-driven? Really, you shouldn't have anything non-driven. If whatever's on the ground, wheel-wise, should be powered in your robot. So that's that. Wheel diameter in inches is self-explanatory. Wheel coefficient, that takes a little bit to get into. If you don't know it, you can leave it as 1.0 or 1.1. Really, all that goes into determining is the pushing current draw per motor. It's good to know how much current you're drawing, but if that's not a topic you know yet, I wouldn't mess around with it too much. I'd get to know, understand the different coefficient of frictions of different wheels, and those should be available on the websites where you can buy them. Alright. Over here, driving gear is the gear that the power is coming from. Driven gear is the gear that the power is going to. So in my intro to gears video, I had a 13-tooth gear driving a 23-tooth gear. So let's say the 13-tooth gear was on our motor, and it was driving a 23-tooth gear. That's exactly how we would show it in this calculator. And this is just going to be a straight up spread of gears that goes 1 gear, 2 gear, 3 gear, 4 gear, 5 gear, 6 gear. So this is how gears are set up traditionally in a, let's say, a single speed. The difference in this calculator, and I'm actually doing this in a bad order because I'm skipping straight to custom 2-speed drive instead of single speed. But if you get this, and the rest of it's easy, so I'm just going by whatever the order the tabs are in. High-speed driving gear and high-speed driven gear, and low-speed driving gear and low-speed driven gear. Essentially the way those work, same as the driving and the driven over on the left. In a shifting transmission, you're going to have 2 gears, high and low, and that's going to be dependent on what you want your speeds to be and what gears you choose. The important thing is, whatever these two numbers add up to be, the high-speed driving and the high-speed driven, the sum of those two numbers needs to be equal to the low-speed driving gear and the low-speed driven gear sum. So in this example, I have 14 and 54 and 11 and 57. I think that was left over from when I was trying a single stage shifter. I'm just going to put this into a more realistic one. Let's say low speed driven gear is 60 and the high gear is 14. Then we have 24 and a 50. That's pretty common. You see over here, just want to show this right here. 2.06 is the shifter spread. Shifter spread is going to update automatically. It's essentially the ratio of your two speeds. It's saying, okay, well, your high gear is 2.06 times your low gear speed, and that's all it means. It's a good thing to know. Too high of a spread can be kind of useless because you don't want your speed to be too high that it's uncontrollable, and you don't want it to be too low that it's useless. So with a super large spread, you can have a very high gear and a very low gear. That's pretty useless. I found a spread around 1.8 to 2.0 is pretty good. Anything more, you really have to have a reason for your gears. But understanding what speed you should be per game is a different video altogether. So maybe I'll go over that later in a different video. Where was I? Yes, okay, some of the gears. So as we went over in the last video, the Gears 101, we were talking about how the tooth count of two mating gears is relevant in their center distance. And in our shifting transmissions in FRC, the way we do this is your high gear and your low gear are going to be right next to each other. In fact, the driving gears for the high and low gear are going to be in the same shaft, and the driven gears for high and low gear are going to be in the same shaft. So if the shafts are going to be the same, that means the center distance needs to be the same. The way you do that is you make sure that the sum of the gears, of the tooth counts, is equal. So that's what I've done here. 24 and 50 is 74, and 14 and 60 is also 74. That's actually one of the spreads for the West Coast Products tool shifter. That's why I use it a lot. And right here we're seeing, going over to the final area of the graph, not a graph, but it's a spreadsheet. Drivetrain high gear free speed, it says 18.93 feet per second. drivetrain high gear real life speed is 15.33, and that's just saying, because we had that speed loss constant over here in the drivetrain efficiency, if you account for all the different errors in manufacturing and thermodynamics and how that works, realistically you're going to gear for almost 19 feet per second, but you're going to get a little bit over 15, almost 15 and a half. That's an estimate. I always like to go by your free speed and just know that you're going to be a bit slower. So these are both calculated based on all the numbers over in the blue section right over here, and it's also calculated using the orange high gear. You have the same thing over here in low gear with the 9.2 low. That's pretty good low speed, and 7.45 real life. Those are calculated with the base, which is the blue over here, and the green. So the base is used in both, but the high gear is used, of course, for calculating high gear, and the low gear is for low gear. Pushing current draw per motor, 58.69 amps. Not preferable. Can work with it though. We'll go over that later on. The only important thing here that I haven't mentioned yet is the ratio, where it says 3.69 to 1 is high gear and 7.58 to 1 is low gear. That's just the ratio of all your reductions, your 13 over 23 and your 24 over 50. That's going to be 3.69, and the same with 13 over 23 and 14 over 60. That's going to be 7.58 to 1. So that's going to be your custom 2-speed drive tab. Pretty self-explanatory. Over to the next one, it's the Vex Pro 3-sim ball shifter. This one's a little less custom, but it's designed to be that way. If you're going to use a 3-sim ball shifter, essentially it allows you to choose your ratios, choose your motors. It's the same characteristics and variables we had to play with the other time. You play with, of course, your wheel diameter, your coefficient of friction, robot weight. The weight on the wheels should always be 100%. Choose your pinions. You have different options here. Choose your low gear option. Choose your high gear option. The external reduction, you can have that in custom. Just leave it at 1 to 1 for now. And here's going to be your outputs. And it's the same outputs as we had before. And this will just show you exactly what you've chosen, just in a style similar to how we present most transmission stuff, like we did in the last one. So that's the custom not the custom, but the 3-sim ball shifter tab. There's a 2-sim ball shifter tab, which works pretty similarly. I'm not going to go over it because it's the exact same way. But of course, it links you to the Vex Robotics site where you can learn more about this COTS gearbox. The WCP DS, the dual, I think it's dual speed. Actually, I've never asked what that stands for. Anyways, yep, works the same way. Leads you to the site where you can figure out what speeds are best. It'll show you which ratios you'd like to choose. Okay, that should not happen. I've actually never used this tab because I always know what data I want to use, so it's the first time you're doing this. Oh, wonderful. You get the idea, though. I guess John just really wants you to use his ball shifter. Anyways, pretty self-explanatory on the speeds and the chosen gearing config, just an output to show you in the way that we're used to seeing. And this also works for the 3-sim DS. Alright, custom 1-speed drive. Actually, I'm going to go over this even less than the 2-speed drive. It's the same thing as the 2-speed drive, only you don't have the high gear and low gear that we had around here. You should have the single reduction stages over here. So I could choose 775 Pro. Okay, that's a heavy robot. 154. Let's say a 4-inch wheel. I'm using a 775 Pro. And we'll say 3 per side. Why not? And I'll cluster them around an 82th gear. Yeah, I'll use that ratio. I'm just showing you an example of how this calculator works. You're seeing all the numbers live update. You don't need to know exactly why I'm doing what I'm doing for right now. But yep, just choosing the ratio. So the first stage is the 12 to 80, and the second stage is the 18 to 54. Just so in case someone's actually confused about what I'm saying by stages, if I go back to the DS picture, you can see over here that the gears from the sim are connected to that big gear in the middle, so that's going to be your first stage. So that's your initial stage. It's going to be 11, 12, 13 to 14 to 42. And all that's saying is that's first stage is from your power, your motor, to the first gear it connects to, whatever gear that is. The second stage, and you can see that cluster gear, the 42 tooth, is on the same shaft as two other gears. That's going to be your high and low gears. So your second stage is going to start on the same shaft as your first stage ends. You're done with that, you just go on to your third stage, and that's essentially how stages work. So the 12 tooth is going to be opinion on the sim, the 80 tooth, on the 775 Pro. The 80 tooth is going to be on a separate shaft. The 18 tooth is going to be on the same shaft as the 80 tooth. And the 54 tooth is going to connect to the 18 tooth, but it's going to be on a separate shaft. So if that makes sense. And coincidentally, I actually did not plan this out. We almost get 13.23 feet per second. Let me see if I could. Really? Oh, no. No? Oh, I have to go up. Come on. Yes. Okay. Much better. I just need a 5/100th of a tooth that I need to add. Alright, that's sidetracking. Anywho. Vex Pro, single speed, double reduction. Works the exact same way as the other ones. Really, aside from the custom 1-speed drive and the custom 2-speed drive, all the special gearbox ones work the same way. I'm not going to go over this because it's you should know this. Like, if you listened to this video so far, you've actually stuck through. Number one, thank you. I can't believe you actually did that. I'm getting bored just listening to myself talk. Number two, if you've listened in that this far, you've gotten enough information on how to use this. So going through the WCPSS, I think that's single speed. Gotta ask RC what those actually stand for. Articulating drive, that is for butterfly drives or octocanum. They work similarly. You're seeing a lot of the same stuff over here, the base motor selection, the speed loss constant, the weight, and all that good stuff. This one's interesting. It separates bumpers and battery. Way to be consistent. Alright, so it says your primary wheel diameter, and that's going to be your base one. Your secondary wheel, and that is the one that's going to be articulated. And you have separate speeds over here, or separate ratios and gears for each one. And you'll notice that in most articulating drives, unless you have a 1-to-1 ratio on your secondary wheel, you're going to have essentially a built-in shifter. So your primary speed is going to be higher, you should be higher than your secondary speed. But that's just how that's going to work. I haven't really used this much for articulating drives. You can essentially solve them as two single-speed drives, which is what you do with most shifters. But this is just a nice way of organizing it all in one place. Alright, now we get to the non-drivetrain useful stuff. That's what I like to play with. First tab is rotary mechanism, which is a nice word for saying anything that spins that's not a drivetrain. So let's say I have an arm or some kind of mechanism. I'd say choo-choo, but choo-choos do not work like this. Mostly arms. Arms is a great example of this, mostly because I can't think of another one. Or 4-bar. 4-bar would work, which is just multiple arms. Choose your motor. Choose the gearbox. Choose the load, and that's going to be the load at the end of the arm. Or, yeah. You just say how far your arm is. I believe these numbers are coming from using this rotary mechanism to calculate friction on a swerve module rotating. Oh, that was fun, yeah. But let's say I had a 20-inch arm, and I was putting 50 pounds at the end. That's a lot. Let's say I'm putting 20 pounds at the end. And that's going to be including whatever robot parts are out there. I put a bag motor on there. I put two bag motors on there. Yeah, two bag motors on there. What's going to tell me is my rotational speed. It's going to tell me the loaded is essentially when I'm putting that 20 pounds on, that 20 pounds of force. That's how fast it's going. No load is just by itself. As you can see, this is going pretty slow. Or sorry, it's going pretty fast. I have two bag motors. They're drawing quite a bit of current per motor, 35.43, a lot more than I'd want in an arm. And the stall load's at 25 pounds, so really it's pushing it right there. So what I do is I would change this to say, no. 84. As you're seeing, as I'm affecting these numbers, the RPM, or the rotational speed, the degrees per second, is decreasing, and the time to move to 90 degrees is increasing. And that's sort of what I want. I want to have a lot of stall load. You can see that's increasing, because personally when I design an arm, I like to keep it at stall. I like to keep it at whatever point I want it up at. So as you can see, I'm going to put quite a bit of gearing into this to get it pretty decent. Bag motors are good for arms. I don't prefer them. I'd probably put a 775 Pro, because these days you just put that on everything. Or you can put a mini sim, that works too. But that's essentially how the rotary mechanism works. I put something off to the side, just my own, in rotations per second. I use that for if I'm doing swerve and I want to see how many rotations per second my module is doing. And then I want to calculate how much load I'm getting from trying to rotate the wheel. But that's just me, that's how I do that. We have two more important tabs, we're almost done. Linear mechanism, this is fun. So this is going to be like an elevator. I actually use this for elevators all the time. Or any kind of extension that works linearly. Translates rotational energy into linear energy. Typical, choose your motor. And we have motors per gearbox, efficiency, travel distance, say it's 3 feet. Applied load. Okay, what did I do this? Oh, this is for a climbing mechanism I made for this year's game. Or I designed one. Never ended up making it. But yeah. So yeah, climbing mechanisms work as linear mechanisms because you're turning rotational momentum into linear momentum. Essentially what you're doing is you're creating a ratio, so as we always have. It's going to show you your no load and loaded. Instead of degrees per second, it's going to show you inches per second, a linear speed. And it's going to show you it says arm time to move travel distance. That's really just time it takes to move that linear distance. It doesn't really say arm. I think you just copied it over. And of course the current draw per motor and the stall load, both of those are way too high for me to like, but I can work with that. Only difference here is something you should know: pulley diameter. That's going to be, it's assuming you're using pulleys to do your linear motion. If you're using sprockets, use the pitch diameter of your sprocket. If you're using gears, use the pitch diameter of your gears. Essentially, what's the effective diameter of whatever's turning to move something linearly? Aside from that, you should be good. The final one, which actually one of my favorites, what I use most often aside from drivetrain stuff, is the intake mechanism. And it works pretty much the same way as the linear mechanism, but it's nice because you get all the speeds and the numbers laid out in front of you. You have your motor selection over here, motors per gearbox. Travel distance, it doesn't affect the load or anything like that. It's just going to affect the numbers it spits out to say how long it will take to move the object. Number of intake sides, 1 or 2. I was confused about this at first But I realized it means how many sides is this one system powering. So if I have this one gearbox for an intake, and I have two-sided intake, but each has their own gearbox, then I'd only say one. If I had a two-sided intake and both were powered by this one gearbox, I would say two. Roller diameters, just as it says, it's the diameter of whatever you are using for your intake. If it's a roller, if it's a wheel, if it's a belt, whatever the effective outer diameter of that is, you put that. Drag load in pounds is really something you have to estimate. You can't guess it. Like for a ball, you're probably not going to have much. If you have like a tote, though, it's something maybe worth testing. Dragging it along the ground with a force I forget what it's called. Yeah, it's escaping my mind right now. It's like, what time is it? It's midnight. Oh, okay, it's not that late. But yeah, drag load, this is just something after you get a few years under your belt, you can estimate. Though, proven numbers are always better. You have your reductions over here, your no-load speed, your loaded speed, and I added no-load feet per second. So it's normally in inches per second. The reason I have feet per second is it's nice to have, it's nice to compare your intake speed with your drivetrain speed. It's usually pretty useful to have your intake moving at least double your drivetrain speed. It's a good rule of thumb I've learned. And then you have, of course, the current draw and the stall drag load. If you do it right, if you have a good intake, you shouldn't be stalling it ever. If you're stalling your intake, something's going wrong. But yeah, that's the basics of that. And there's the very last tab. It's just the data tab. It's where the calculator pulls all of its numbers from. You can add your own stuff in there if you'd like. For example, I added in a 775 Pro at 6 volts, and none of these numbers are correct because I just assumed that if you have the voltage, you'd get half the results. That is not the case. I didn't know motors at that time, and I still have not fixed it. I will get to that. But yeah, this page you really shouldn't mess with. So aside from that, that is the JVN Mechanical Design Calculator. I hope you learned how to use it, and I hope you learned something pretty well from this. Oops. It's an amazing tool to use if you understand what you're doing with it. And I'm hoping that my students, anyone who watches this, can use this tool to learn how to better design robots, and more importantly, design robots that work the first time. Thank you very much for watching. See you next time.